Thank you. I decided that I would stand here and give a presentation like that because it's better that I play with the computer than he does. But I think it'd be okay. You won't suffer having to look this way. Not too much, okay. So basically, I initially was under the impression that I would have like 45 minutes to talk, and then I was told, well, actually it's like 20 minutes, but by that time I'd written the talk, so I'll try to do it in half an hour, and I think it'll work out. I'll just skip a little bit and maybe not tell you as many stories about the characters in play there as I would have done otherwise, but I will start briefly with the sort of history of how we came to be where we are, a little bit of physics about atmospheric physics, what is behind the greenhouse effect, and then tell you a little bit about what we've been doing, how we have been able to enhance this through experimentation with the atmosphere that was not planned. And I will also then delve into a little bit about fiction versus fact. I have actually a different lecture on that. It's a lot of fun actually to look at these sort of different claims against the science of climate change, and you can sort of have fun with that. I've done that a little bit, but I think I picked 2 or 3 examples from that. And then we'll talk about projections, sort of what is this leading to, and in the end, sort of the meaning of this, which actually is probably what we should be talking about only, but I'll start with the rest first. Now, people have been thinking about the atmosphere, of course, for a very long time. The oldest writings are from Sanskrit, 800 years before Christ or so. In this one, the main character actually I want to point out is this guy who has his picture there. This, of course, is drawn, but he is also the first known inventor of a pinhole camera. Probably more people have invented that, so it's fitting that he should have a picture there. But he's known in Arabic as Ibn al-Haytham, but in Latin, his Latinized name was Al-Hazan, and he wrote a book on atmospheric optics, in which he actually showed an experiment to figure out how thick is the atmosphere. And the impressive thing is there is not the number he arrived at, but which is probably like 40 kilometers. Actually, people aren't really sure what his version of Passum meant, but sources disagree on that. But basically, the idea is simply that the atmosphere is finite in thickness, which is a pretty impressive idea. And being able to actually figure out that data shows you that the atmosphere is finite in thickness. Another thing remarkable about him is that he was one of the first empirical scientists. His view of, for instance, Ptolemaeus and Aristotle was, these people, they were men, so you should treat their text like any other man. Doubt it and try to verify it. And therefore, when he wrote things, he said, here are my experiments, repeat them if you can. So he's well liked by many scientists and have been one of the first sort of empirical scientists. Now, the point is, once you figure out the atmosphere is of finite thickness, then 200 years passed until people were actually able to measure pressure. There was a guy called Torricelli in Italy, and more importantly, he invented basically the barometer, but Pascal in Paris invented a better version of it. And Pascal thought about this: if the atmosphere is finite in thickness, it should actually decrease in weight. The pressure should drop as you go further up, at least if his theory about the nature of pressure was right. So what he did is he devised a barometer, sent it to his brother-in-law, whose name was Florent Fourier, and he lived in Auvergne, in a city called Clermont-Ferrand, and said, could you take this out and scale the mountain Puy de Dôme, which is just outside Clermont-Ferrand, and measure if the pressure drops as you ascend the mountain. And he did that and found out pressure was dropping, and therefore it sort of showed them that their ideas they were getting a foothold of understanding the atmosphere. Then a long time passes, and in the 18th century there's this another French character called Horace Benedict de Saussure, who is famous mountaineer mainly, but we sort of celebrate him as the first mountain meteorologist because he would climb mountains with enormous amounts of gear on his back. Or actually, I suspect that his assistants were carrying it. He was, after all, a nobleman. But there is a statue of him in Chamonix because he's the first person with Balmat to climb Mont Blanc, so you know of. And here's a picture of him. I don't know where that statue is, but you can see that he has a gadget on his back. And one of the things he devised was an instrument that he called heliothermometer, which was a hot box really. It had like one transparent side, and he would hold it up against the sun. The rest is all black. And it's very well insulated, so then he would measure how much is the sun heating this chamber inside. And his idea was, because he had a very simple question: as you start climbing mountains, you have to wonder, why is it so cold up on those mountaintops? Why isn't it, warmer? And so his first idea was probably the sun is not as strong on mountaintops as it is below. So he devised this instrument, and it showed him that actually the sun was stronger on mountaintops than it was below. So the atmosphere gets in the way. So he didn't had no way of explaining this, and the explanation was given by a guy called Fourier. Fourier is the person who sort of coined the explanation that we have for the greenhouse effect. And in a fairly incomprehensible, Fourier is one of the greatest names in physical, mathematical physics. He sort of developed the field in many ways. You cannot get any degree in technical university without getting through some of his methods. And your cell phones wouldn't work without him. So he's a big character, but I was really surprised when I read this monologue that it's totally incomprehensible. And it's just the style is so flowery. But basically what he says, and he pins that what happens is that the heat has an easy way of passing through the atmosphere being in a state of visibility, meaning being light. But it's very hard for the heat to escape once it has been transformed into what he called chaleur obscure, which means invisible heat. The current version of this, so basically his explanation, he actually cites Horace de Saussure and says, here's the explanation of this, and actually the atmosphere works a little bit like his box, his heliothermal. But that also brings us to a question of dust and the thickness matter, so it brings us back to Alexander. Before I answer that, I'm trying to give you a modern version of Fourier's explanation, and it would go like this. I once made this for a group of parliamentarians. It's called Greenhouse Effect in 1 minute, and they didn't understand it, so I repeated it. But anyway, so basically it goes like this. Everything that's hot, and hot here means colder than minus 273, so that means us and the rest. Everything will emit heat, radiation. The sun is really hot, it's 6,000, the photosphere is about 6,000 degrees Kelvin, so it emits a lot of radiation, and that radiation is visible. And it penetrates the atmosphere quite easily and heats the ground. About half of it actually is lost. Some of it is absorbed in the atmosphere, the rest is radiated to space, but about half this energy comes in and heats the ground. And it's not too difficult to calculate what the heat of the planet should be based on this. And you get a number which is about 33 degrees too low. The average is like 15 degrees and you get minus 18. So if that was true, then we would not be here. Now, what happens is that as the ground is heated by the sun, the ground will start emitting, because everything that's hot emits. So the ground will start emitting heat, and this heat has a totally different wavelength than the solar heating. And the atmosphere is not transparent in that wavelength. The atmosphere is opaque, and so it absorbs it. And when the atmosphere absorbs it, then, because everything that heats, the atmosphere will heat up by absorbing it. Everything that heats will emit heat. So the atmosphere starts emitting up and down. And the stuff that comes down is what we call radiative forcing, and that is basically the essence of the greenhouse effect. I should add here that the greenhouse effect is a complete misnomer. Greenhouses don't work this way, but it's too late to change the name. So the balance sheet, I'm not going to go over that in any detail. The main point is that this effect is really strong, and if you do the numbers, you find out that this back radiation, which is like reutilizing the heat from the sun, is actually twice as effective as the energy from the sun. But we'll jump over that. Now, so back to atmospheric thickness. When Fourier had written this stuff, people were beginning to realize there had been ice ages, and there was actually Horace de Saussure has sort of played some role in that discovery, and his crowd. But then they said, how can we have had ice ages? What made the atmosphere so cold? And they thought, well, maybe the atmosphere was sometimes thin, sometimes thick. But there was this guy called John Tyndall who measured, basically said, well, it could be either that or it could be composition of the atmosphere. And he did some experiments and he found out that there were two gases that were really responsible there: water vapor and CO2. Tyndall, he was Irish, great believer he was Irish Protestant and completely against Irish separation, and apparently was proud of having coined the slogan, "Home rule is Rome rule," which I don't think works in his credit these days, but this is one of the things he was proud of. But he is mainly, in my field, known for being a brilliant scientist, and he wrote this sentence that you can basically read quite easily. It is not therefore necessary to assume alterations in the density and height of the atmosphere to account for different amounts of heat being preserved to the Earth at different times. A slight change in its variable constituents would suffice for this. Basically change the composition of the atmosphere a little bit. And you can do all sorts of stuff. And then he adds, such changes may in fact have produced all the mutations of climate which the researches of the geologists reveal. Basically saying, so this was the ice ages. Okay? Now, the thing is, you can measure this, and this is the diagram I'm going to show you here. It's, if you have a satellite that flies over the Earth and looks down, they can actually see this, you can measure this, and if the atmosphere did not behave this way, all the lines you would see would in this case follow the dotted line here, but instead you measure something with heights and valleys, and you can, if you know a little bit of physics and have the right computer programs, you can work out what each of, that these are signatures of different chemicals in the atmosphere. So without the greenhouse effect, you wouldn't have measured this. So basically, this is incontrovertible. Now, the last person I'll mention here is this guy called Svante Arrhenius, who tried to calculate what effect, how much do you have to change CO2 to get an ice age? And he came up with, if I reduce it by 60%, I get enough cooling in Sweden to cause an ice age. And then as a sort of, because he was doing this anyway, what happens if I increase it by 50%? And then, no, if I double it, sorry. And then he realized that he would get warming by about 4 to 5 degrees. So he is the first person to actually run a climate model, but it was actually wrong in many ways, but the answer was right, which is always, it's very good to be creatively wrong that way. So what has happened since then? Well, we know that the chief gases are, as I say, CO2, and since then we found out that methane and N2O are also active. They've been increasing since 1750, which is sort of before before we started burning coal, the Industrial Revolution really. And most of the increase is due to burning of coal and oil and gas. And one consequence of that, which I won't mention, is that the oceans are getting more acidic, and that's a different talk, I would guess. But it's a very serious issue. Now the thing is, I told you that we have a name for this radiation that comes back from the atmosphere. We call it radiative forcing. And we can measure how much, if we know how much we've emitted, we can calculate how much radiative forcing has actually increased in the last 200 years. And this shows that it's not a friendly graph. The only thing you have to look at are the 3 lowest bars there, which show you, 1/2 a watt up to 2.6 or 2.3 watts. And this is 1950, 1980, 2011. So you can see how rapidly we are increasing this. And the numbers are basically watts per meter square, and I used to tell people to think of, hot light in a room or something, but now we switched over to those LEDs, and nobody remembers how hot the lights used to be. But basically, it's a lot of energy that we're putting on the planet. It's equivalent to a nuclear bomb every few seconds, basically. So once you increase this, you're going to get global warming. There's almost no way about that. And these pictures show that. And the line here basically shows you how temperatures have increased from 1850 to 2013. The map shows you the increase in temperature in the last century, and you see basically the story is almost all of the globe got warmer. The continents got warmed more than the ocean, and the only part that didn't really warm is a region just south of Iceland, in the ocean, which is behaving in its own peculiar manner. Now, then we come to the fun part, the skepticism and denial. I used to have this Donald Trump as a joke and everyone laughed, and nowadays nobody laughs. This is getting too serious, but I collected these sort of nice little, it's the Church of Climatology with Al Gore and money sticking out of his pocket, and there's a green choir behind him, and you have Oprah, it's a talk show host, and you also have Hillary Clinton singing there in the background. It's quite sort of nice. And then of course global warming is a hoax and so on. Standard stuff. One group that says this, they have various lines of claims, and one is that actually increasing CO2 doesn't matter, the atmosphere is saturated. And that comes from various people that have picked up here two sources of this. This guy in the lowest corner here is called Fred Singer. I once heard him give a talk, and afterwards I summarized the talk it was like saying to someone, you lend someone tools, something to do with your shed, and then he returns it. Let's say it's a rake, and the rake is broken, and you say, well, it's broken, and he would say, first of all, it was broken when you gave it to me. Second, there was nothing wrong with it when I returned it. Third, I never borrowed it. And so any of these arguments would do, but in a sequence they don't work. And that was a little bit my feeling with the lecture by Fred Singer, but he certainly gets a lot of money for talking. But basically the claim is that the sea atmosphere is saturated. And the point is, this used to be a scientific point, a valid point actually, made by Angstrom against Sancta Arrhenius. And they basically did some measurements, and they found that when they increased CO2 in a tube, it didn't affect at all the transmittance of heat radiation through it. So they said, okay, the atmosphere is saturated. And it took a long time for science to realize that this argument is complete nonsense. It doesn't really matter, because what matters is the atmosphere gets thinner and thinner as you go up. At some point it will not be saturated, regardless of what happens below. And at that point, the greenhouse effect warming will occur, and that warming will then be transmitted downwards. So it doesn't really matter. Second of all, of course, the measurements were somewhat bogus, but still this thing has propagated and is still being played, even though it was disproven more than 50 years ago. Probably about 70 years ago by now. You can also measure the change in the spectrum here. I'm not going to go over that in any detail, but you can basically see the fingerprints of atmosphere, of CO2, having impact on the radiated balance of the planet. Now, warming is the next argument against this. Just some nice headlines here. And it's often supported with a graph like this, saying, there's not been any warming for a very long time. And you also have this sort of Supertramp thing. It's a good album, Crisis, What Crisis? Why, there's no warming occurring, why are you complaining? This is often played with a recent story about the hiatus. The hiatus was this idea, if you look at the plot here from 1980 to 2010, you can see the planet is getting warmer. This is global temperatures. But if you look from 2000, so the very right part of this, it looks rather flat. So it looks like it went up and then became flat, okay? And that's what's called the hiatus, meaning nothing was really happening, or we expected something that didn't really happen. And the point is, this got a little bit more airtime than it should have, because it's a very short period, and it's very hard to get significant trends on that period. And people didn't ask themselves the right question. So the person who actually looked at the right question is the guy called Foster, who blogs by the name of Tamino, and I once got him to do this plot that I'm going to show you here. So basically, it works like this. Let's plot temperatures from 1975 to 2000, when the hiatus is supposed to have started, okay? We get this. Straight line through it is this. We know what the slope is. We can do some statistics and say points should fall within these dotted lines. The narrower band should be 66% of the points, the 90% of the points between the extra bands, other ones. So this is just the past. Now, if we continue these lines, we haven't done anything except say, if nothing has changed, then the future should more or less follow that line and be within those points, in that range. Now, if planetary temperatures have veered off, we will notice because it'll go outside the range. Okay? So let's do that. This is the next. So this is the hiatus time. So basically, the data does not give you any evidence to refute the hypothesis that the slope has changed, basically. So the slope is unchanged, basically. So basically, you cannot say the slope has changed because you don't have enough data to do that. Now, of course, you can add the last 3 years into this since we did this, and then you can see that temperatures have risen. So the slope is changing, but in the wrong direction. So it is actually getting warmer. Now, okay, it's warming, but it's not man-made. That's always a favorite. And the last person to say that, who is by many considered completely sane, is this new head of the IPA in the US, Scott Pruitt, who said, I think that measuring with precision human activity on the climate is something very challenging, and there's tremendous disagreement about the degree of impact. So no, I would not agree that it's a primary contributor to the global warming we see. He said this last week, I think. And the point is, we know that this is wrong. We have two lines of argument, both fairly strong. One is called fingerprinting. It's when you run a model with all the forces that have changed, greenhouse gases and everything, then you run it again, but don't include the greenhouse gases, but run the cooling things like volcanic eruptions and so on, and check what happens. It turns out, only when you include all the forcing can you simulate climatic evolution, But if you throw out the man-made effects, you don't get the warming of the last 60 years. So that is very conclusive evidence. You can also do statistical analysis of this. And there's a different group that does that, completely different technique, and they get the same answer. So we can claim without much hesitation that we are certain that most of the warming in the last 60 years is due to human activity. We cannot say 100%, but you know, it's up there. Definitely more than half, and probably more than 80%. So, then we're going to briefly talk about the impact and where this is going. This is the IPCC, and of course, even if I didn't have temperature data, I still would know climate change is occurring because the evidence is completely overwhelming. There's so many things changing, and this is the IPCC sort of summary statement in 2013. Warming of the system is unequivocal, changes are unprecedented, many observed changes are unprecedented over millennia, or decades to millennia, basically. Now, so how do we then, when we think about the uncertain future, how will it go? The problem is we don't really know how much we're going to emit. You know, we could all agree to follow Paris and emit little, or we could agree to just, you know, say fuck it and just burn as much as we can. And it sort of seems like we're heading that way right now, but we probably will change our mind at some point. So what we would do is we come up with stories, which we call scenarios. Scenarios are basically stories of how much we will emit. Then we take those stories and we plug them into models and we see what happens. And in these stories, the red thing will always mean a hot scenario, and the blue thing will always mean a cold scenario. So here is what you get. This is actually warming until 2300, but the main point is that the warm scenario should warm the planet by about 4 degrees towards the end of the century. The cold scenario should be about 2 degrees, a little less than 2 degrees actually, and other cases are in between. But this is not uniform. So here's a picture of this, where we've taken all these scenarios and we just plot what is the proportion, which area warms like the average, which areas don't. So things that are yellow to red on this warm exactly at the rate the planet is warming. Things that are dark warm faster. So what you see is, you expect the high latitudes of the north to warm fastest, almost twice the average of the globe. You expect continents to warm faster than the oceanic areas, and oceanic areas to warm slowest. And this sort of, you know, it's not very surprising, is it? You can do the same thing with precipitation, and then you get less, the results are not as conclusive, but basically the story with precipitation is that you expect areas that are already dry to become drier, areas that are already wet to become wetter, and precipitation, when it falls, it doesn't show it in this graph though, tends to be more intense. Okay? So, I'm going to skip these things here and just mention a little bit about global sea level rise. Another thing that's also going to happen is that sea level rise is going to occur, and it is by now it is simply not avoidable that it will increase by several tens of centimeters. The guess, it goes from probably something like 60 centimeters to 1 meter at the end of the century. We know now that there are parts of Antarctica that are probably starting to collapse, meaning that you have small ice sheets which will, in the next few hundred years, go away. By that, they will be raising sea level by a few centimeters a century. That's maybe not that worrisome. What is really worrisome is that when they go, they may be buttressing bigger ice sheets. And if all of that goes, then basically lose most of Antarctica, we would be raising sea level by 5 meters in maybe 500 years or so. And then we haven't said what's happening in Greenland. Okay, so adverse impacts accumulate with warming, and this is a picture of that. The two scenarios I plotted there, the warm one and the blue one. We can think of the blue one as being the Paris Agreement. It's actually slightly colder than the Paris Agreement. But so if we were to implement Paris and stick to it, we would be warming a little bit more than the blue line there shows. The envelope of the blue line is sort of the level of disagreement between different models. So you can think of that as the uncertainty. So there are sort of two sides of uncertainty. One is what are we going to burn? And the second one is once we know how much we're going to burn, there is always going to be some uncertainty in predicting how this is going to go. To the left, right here is a picture of various systems, and they are either, yellow means moderate amount of damage. The red means a lot of damage, blue means high risk of damage, and it's basically a thermometer beside it. So once you get to 5 degrees, most of these systems, which are threatened systems, actually deal with extreme weather, various impacts, global aggregate impacts, large-scale singular events. These are all buzzwords for bad stuff happening, and basically the more you warm, the greater the likelihood of something damaging happening, which maybe is not that surprising. So finally, I'm just going to end with this here. What do we do with this information? I often get this say, so you believe the globe is warming, and I don't know, I don't believe it. It's, it's totally irrelevant. What I believe has nothing to do with it. It's a little bit like going back to Al-Hassan. Here's the data, look for yourself. I don't have to believe this. This is a fact, it's occurring. So it's, I haven't really told you what I believe, This is simply, so science doesn't work that way. You can't really discuss it as it is a matter of opinion. So then the question is this a scientific issue? And from my point of view, no, it isn't. I admit it's a technical issue in many ways. Many of the solutions are very technical. You have to work out their impact and so on. I often talk with economists who have various technical points of view on this. But my point is really that I think this is an ethical issue. It's not a technical, it's not a scientific issue anymore. The science has sort of done its part. Okay? So the second thing then is what to do with this information. Climate change touches on several very different ethical questions. One, the obvious one, when you look at this, the one that yells at you is that areas that are hot will get hotter, you get more heat waves, more damage from heat waves, which they are damaging already. Areas that are dry are going to get drier. So think of hot, dry places, they are definitely not the places we want to settle in. Now, the places that are like that are usually places that are populated with nations that have little adaptability but are very dependent on climate-related goods. So then it basically boils down to rich versus poor. Is it acceptable for rich people to do something that will hurt people far, far away? That's the immediate thing, and I think we all agree that the answer is not yes, but no. But then it's also the present versus the future. There's a lawsuit, I think, in preparation in the US where the generations of the future are going to sue the president, which I find kind of funny. But this is the US. They always take everything to court. But it still is a valuable question. I mean, how ethically defensible is it to sacrifice future generations' well-being for our own sort of economic benefit? And then the third one is humans versus other systems. Natural systems have been here for a very long time, far longer than humans. And it's really amazing if you think of it, does anything give us the right to wipe out a lot of species, because this is going to wipe out a lot of species. It's sort of almost beggars belief if you look at the sort of enormity of the problem that we're causing, that we have any right to do this. So that is question number 3 in the sort of ethical sphere here. As an aside, I should say that nature has a way of correcting for these things, but the correction is not necessarily something we want to experience. So that pretty much ends it. This final graph here, and I'm still under 30 minutes, the final graph here is a graph that came out of running a lot of climate models, and it's one of those, what we call emergent constraints. It's something that happened and no one planned for this. This is not something that was built into the models. It just, when they started looking at it, they realized they had this beautiful relationship here. And I'm going to explain it a little bit. This here is total emitted CO2 since the beginning of the Industrial Revolution. So we are now at about 500 gigatons. We're doing like 33 per year, just keep that number in mind. So in about 15, 20 years, we can actually go up to 1,000. Okay? Now, this is the temperature anomaly relative to beginning of the, or sort of relative to when we have good data, which is 61 to 80, 1861 to 80. And the black points are basically the global temperature, which has been oscillating here, and they mark it, the temperature versus how much have we emitted. Okay? So we are here, 2010 we're here, and these are the different projections, these lines I was telling you, and it so happens that they all form on a line which pretty much follows this. So we can think of this as a fairly good you don't really need anything very complicated. We can just say how much we're going to emit. Give me a number here, okay? Somewhere between 500 and 1,000. Circle here 750. Okay, 750. If we go up to here, we say, okay, well that's warming up about 2 degrees. If we are really lucky, we can emit 1,000 and still stay sort of reasonably close to 2 degrees. But going above that, we're not going to be below 2 degrees. Now, here's the point. If you do this number, you look at, so we can emit a maximum, say 500 gigatons per CO2. If you look at how much is on the books of oil companies, how much oil do they claim to have found but not used, it vastly exceeds that number. So the bottom line is actually, if you own stock in an oil company, sell it, because A, it's unethical, but B, also, most of the oil that they have on their books cannot be burned, because doing so would totally wreck climate. So almost all of the value of oil companies, which is the oil they have in the ground, is worthless. And I think I'll stop at that.